Well, so I'd like to get started. Welcome, everyone. This is our final colloquium of the semester. We're very lucky to have with us Emily Chin from the Scripps Institution of Oceanography. And so Emily is an interdisciplinary petrologist. She's interested in the evolution of Earth's lithosphere, and she comes at it from a lot of different angles. She started at Tulane. She actually grew up on Long Island, so she's from the greater area. And so welcome back, Emily. But then she got her PhD working with Cynthia Lee at Rice, did her postdoc at Brown, and has been at Scripps since
2016.
2016. Yeah. So thank you, Emily. We're looking forward to it. And she's an MSA distinguished.
Great. Thank you, Ben, and really happy to be here today. So I'm going to share some recent work that I've been doing that kind of is in an idea stage, largely. So some of this has been published, but I really welcome feedback after this talk. So, I think the most exciting thing about visiting other places is to expose some of the ideas one has and then get feedback. So I'm really excited to share the story about how Cratons become strong and how they stick around for a long time. So what are Cratons? Cratons are defined as the core regions of continents with very thick mantle roots. And in some cases, these mantle roots can extend to over 200, 300 kilometers deep. The Cratons are all thought to have formed in the Archean to mid-Proterozoic, so they're ancient. And they're still around today. So this is a map of the Cratons that are still in existence. And as you know from plate tectonic theory, when we have very thick old lithosphere, as in the ocean basins, that lithosphere should be unstable and should subduct. So the why Cratons have stuck around has been an intriguing question for petrology and solid earth science for decades. So although in general Cratons are stable, as in they've survived billions of years, they're not necessarily without activity. And we know this because this is a map of the cratonic or lithospheric thickness from a seismic velocity model. And these dots are showing kimberlites that have erupted over Earth history. And you can see that all of the Cratons, well, except for Antarctica, probably because we can't sample them, have evidence that magmatism has actually ruptured through this very thick mantle root. And in many cases, those volcanic eruptions, those kimberlites bring up valuable pieces of the mantle called xenoliths, which forms the basis of a lot of what I study. And these fragments of the mantle are really our only direct pieces of the deep lithosphere. So many of you in this department study meteorites. We kind of think about meteorites as xenoliths from space. So this is sort of our only direct evidence of something that doesn't get exhumed tectonically. So one of the things that has plagued mantle geochemists and high temperature petrologists who work on mantle rocks is that we can't really date anything in the mantle very well. And that's because most mantle rocks at the depths that they reside, if we go extrapolate the geotherm, they would reside above the closure temperature of most isotope chronometer systems. Also, when these xenoliths erupt through kimberlites, the kimberlite itself, if you've ever seen a kimberlite thin section, it's a very chaotic rock. It's a very volatile, rich eruption, and that process may itself also heat and overprint the mantle that it samples. We also have the problem of metasomatism, and that can also obscure any sort of primary signal of when we had a deformation or a melt depletion event. So a lot of my research in the last several years has focused on, so I am technically a geochemist, but I've really branched out into using a lot of different tools that are complementary to geochemistry. And one of the important data sets is to understand the textural and microstructural sort of evolution of mantle rocks and how that ties into the geochemical evolution. I'm going to talk a bit about microstructures, the fabric of mantle peridotite, and how those fabrics can inform us about the geochemistry. And the tools that I'm going to use for this are large area mapping of xenolith thin sections using EBSD. So this is stands for electron backscatter diffraction. It's a method that can measure the crystal orientations of grains in a solid sample, and it's based out of an SCM. So you can attach these detectors to SCMs. And I'll show some, if we have time, some data that involves looking at the volatile contents, particularly water content and trace elements in mantle rocks. Okay, so we're going to take a step back to a very old paper that anyone who's looked at the textures of peridotites has probably been familiar with. This paper by Mercier and Nicolas in 1975 was the first to look at hundreds of peridotite xenoliths from all around the world, all different cratons, and also off-craton areas. And they classified the textures that they observed into 3 different main textures. And then they mapped, or they put those textures into what they envisioned for a deformational cycle in the mantle. So this could be, a short-lived event where if you even have a shear zone in the mantle, you might evolve this textural. But it can also be a long-lived thing, so it could happen over much longer time scales. So the main goal here is to take this old concept and kind of revitalize it and use it to map to tectonic and geochemical events beneath cratonic lithosphere. So just to explain what this cycle is, and these are just very boring black and white sketches to show you the key features, and I'll show some actual thin section photos in a few slides. But the first texture that was identified is this very coarse-grained, what was called protogranular texture, denoted here. And it was thought that this texture results from recrystallization of a precursor peridotite that was depleted by partial melting. So you think of peridotites as metamorphic residues of mantle adiabatic upwelling, where that mantle has been melt extracted. That melt goes on to be basalt and then erupts, becomes crust. What's left behind is a cold, dense residue, and that residue will have this texture and will eventually recrystallize. So now what happens if you take that background mantle lithosphere, and you deform it? So if you subject that mantle lithosphere to some plastic flow high stress event, you'll get a texture that looks like this, where you have a very bimodal distribution of grain sizes. The smaller grains are going to be mostly olivine that have a lower viscosity than the larger pyroxene grains. And if you take away that deformation and allow the mantle to recover, then eventually the strain energy that's stored in all those grains is going to want to reach a more stable state. Grain boundaries will adjust to become more 120-degree triple junction. So if you've seen these very equigranular textures in lab or in the field, you know that this is something that we think of as textural equilibrium. So what do these look like? These are some real-life photos, and I also included, for reference, some of the really nice original sketches in that 1975 paper, because I think these sketches are also very illustrative. So if we look at the protogranular texture, the key feature of this texture is a very coarse grain size, up to about 1 centimeter or greater. So this is a thin section scan. This is an entire thin section, so this is 46 millimeters. And you can see that many of these grains are approaching centimeter level. You have curvilinear grain boundaries with some polygonization, and you also have subgrain boundaries. So a subgrain boundary is where you have internal lattice defects of a mineral that stack into stable configuration. So this is stored strain energy. So this rock actually would have a strong fabric and actually has evidence of being deformed. But overall, when you look at it, there's no, at least from the thin section xenolith scale, there's no clear macro scale foliation. So now if we move to that texture where we have deformation active, this porphyroclastic texture, this is a really cool example from Baja California that was collected by a former postdoc at Scripps, Rachel Bernard. So this shows this classic bimodal texture where we have strongly bent and deformed pyroxene grains and the recrystallized olivine grains. And then finally, when we take away that deformation and allow recovery and recrystallization, we can evolve the mantle to this equigranular texture where things are at textural equilibrium. Okay, so those were kind of the three main textures that have thought to be evolving in the mantle over time. But there's this one other texture that has been pointed out by the authors of that 1975 paper, but has not really received a lot of attention. So a large part of this talk will be bringing awareness to this texture and what it means geodynamically. So that texture is a subtype of the porphyroclastic texture. It's called transitional. And like the porphyroclastic texture, we have this very strong bimodal grain population. But the key difference is we have these olivine tablets. So these are olivine grains that you can see here. And if you look at their color and cross-polarized light, they have no subgrains. They're basically strain-free. And you can see in many cases they're growing into porphyroclasts that have a lot of subgrains, so more deformed grains. So we'll come back to what that means in a little bit. So why do we care about this? So the reason why textures are important or useful for understanding geochronology, if you will, in the mantle is because there's a time component to the evolution of those textures. So if we think about dynamic recrystallization, so this is a process where we have deformation, plastic flow, and we have recrystallization ongoing. So it's like, think about the grains are fighting the stress the shear that we're putting on them. And this also will occur after we take away that stress to some extent through static recrystallization. So in this top example, for instance, so this would be, if we go back to the example of the tablet grains, if we have a very strain-free grain, that's actually a very stable configuration. So if we look at the conceptually what the dislocations inside that olivine crystal look like, that tablet would have very few. So that wants to grow out. It's stable. It wants to increase its surface energy. And so these sort of grains will want to grow out into the higher dislocation density grains. And that process takes time, grain growth. So this is what we would call a grain growth mechanism. So this is kind of what I'm getting at, where we can, and this sort of concept I think is still in its infancy because a lot of this data comes from the field and also experiments, and not a lot of it has been tied to looking at things like xenoliths and meteorites just yet, but hopefully I'll inspire some of you to think about how we can do that more. So what will we do in this talk? We will go back to that old mantle deformation cycle, which I'm sure lots of people have used and just kind of used as a classification tool. But we're going to put that now into the framework of how Cratons actually built and is evolved and modified over time. Then we'll focus on this transitional texture and what the importance is. And if there's one takeaway or two takeaways I want you to take out of this talk is that this texture, which is something that we haven't recognized before, when it's actually captured by a kimberlite in a xenolith, indicates some high temperature event that happened very recently that geodynamically made that lithosphere unstable. But if it's not captured by a kimberlite, so we can imagine many kimberlites probably never erupt because thinking, how do we get magmas to go through 300 kilometer thick lithosphere? As far as I know, no human in known history has ever observed a kimberlite erupt. Or if they did, they didn't survive. So there's probably many kimberlites that essentially failed to breach to the surface, but they still will modify the base and margins of the cratonic mantle. And that's kind of something that I want to introduce as a concept of how do we sort of discern that. And then if we have time, I'm going to show some data from the Wyoming Craton that kind of uses these concepts as a case study. Okay, so let's go back to this Craton deformation cycle. So I'm going to set up a series of schematic sketches of how I think Cratons form, what textures are formed, and how that plays out in their stability. So some people in this room may disagree with this because I think this is still an active area of debate, how Cratons or how continents, Archean roots form, whether they form by some non-plate tectonic process like plumes that melt and then leave behind thick residues, or whether there's a plate tectonic-like process involved. So I'm of the camp that some sort of tectonic-like process was very active early on in Earth. And maybe it's not like what we think of today as normal cold subduction, but we had plates moving around and we had accretion and suturing of different small microcontinent blocks together to basically make thicker lithospheres. So that process would, create this protogranular texture because we would have melting of the mantle, maybe in ridges, that leaves behind residues. Those then move around to some extent and accrete onto larger blocks to build out cratons. And we see this, right, in North America, like the Laurentian craton has built out into the Proterozoic over time, and we would consider everything, that's not even Archean to be sort of that old cratonic area. So during that coming together phase, when all these discrete blocks are coalescing, amalgamating, this is where we get the deformation that probably has to occur through some localized areas in the craton. So I'm going to go with the idea that shear zones can extend deep into the mantle, and those are what localize this stress so that we can actually facilitate deformation and suturing. So that would be the development of these porphyroclastic textures, so I should mention, in every xenolith eruption suite, in all cratons, we get we get all of these textures, and in some kimberlites we get more of one than the other, and that itself is a very interesting observation. So after that deformation stops, and let's say now we have a thick lithospheric cratonic block, that texture will evolve to equigranular textural equilibrium. We could stop here and let's say this is just our craton for the next 3 billion years, nothing happens to it. But we know that's not the case because we know kimberlites have erupted. And I think of kimberlites as damaging the cratons in a sense because they are a modification of that cold lithospheric keel. So when we have kimberlites that have damaged the craton, some of them successfully erupt, but the ones that don't will result in these transitional textures, which we'll come back to. So this process of damage, metasomatism, kimberlite eruption, it doesn't have to be kimberlites, it can be alkali melts, low degree melts that are interacting at the base of the craton. That is a damaging process. And eventually, we know that over time, this has not broken up all the cratons. They've survived. So they've come through these traumas and healed themselves. There's probably scars. But in some ways, we know many kimberlites never erupt, and they probably have modified that texture to make it stable in the long run. So this is kind of what I'm thinking as a conceptual framework. And a lot of my future work and ongoing work is interested in kind of exploring aspects of this cycle in more detail. Okay. So we're going to now march through some of these different steps, how we build a craton, what textures and geochemical, petrological information we can get from this sort of combined view. So let's talk about building a craton. So the key thing about building a craton is we need to thicken the lithosphere somehow. So we can do that by just, cooling a thick lithospheric root like a plume head residue. As it cools down, it gets dense, it gets thicker. But there's evidence from peridotite petrology. This is work that Cinti and I did in 2014, where we were able to use magnesium and iron partitioning in whole rock peridotites, filtering through for peridotites that have been significantly metasomatized, and we looked for the ones that are truly residues. We found that the pressure and temperature of melt depletion of these peridotite xenoliths was a lot shallower in some cases than the metamorphic final equilibration pressure and temperature. So that's shown in these colored symbols. The tie lines connect exact samples just to illustrate some of these. So what this suggests is that the mantle melted shallower to form these residues in the Archean. How shallow is still up for debate. Is 5 GPa shallow? Maybe. And we would form that initial protogranular texture. And we had to have some path that took that initial mantle residue down to higher pressures and cooled it. So this is a thickening path. And if we imagine what that kind of looks like in our minds, this would have to involve some deformational shear zone activity and then a final equilibration at the colder temperatures and higher pressures that are where these future xenoliths reside in the mantle root. So this just highlights that during that amalgamation phase of craton formation, I think the lithosphere needs to be weak enough to deform. And this is a really big question. The question is, do we see evidence of that in the rock record? So I think we do, possibly. So if we look at the western US, so this is the Wyoming province, seismic images have shown there may be remnant oceanic lithosphere, what is thought to be high velocity cold lithosphere that is stuck and has these dipping reflectors seismically. So this is thought to be perhaps something that could be explained by this process of accretion of different cratonic microblocks. So basically the main takeaway from that is that we need shear zones to facilitate this. And this is just a plug for some of the recent work that Rachel Bernard, who's a postdoc I supervised, recently published. This is actually looking in the deep lower crust beneath Baja California, which is an active strike-slip boundary. But to make a long story short, we found that there was an important interaction between melt or petrographic evidence of melt and how the fabric of lower crustal rocks actually changed as we deformed them in the presence of melt. So we haven't really figured out or seen that exact analog in the mantle, but I want to highlight, we know mantle shear zones can extend to moho or even deeper depths, and we know this from looking at the San Andreas Fault and the Western California margin. And xenoliths like this that erupt, so this xenolith erupted sometime in the Holocene, and it was sourced from Baja California. So we know this is off-cratonic young mantle, and look at how deformed it is. So there's strong evidence that there is deformation that can go deep into the mantle, but it has to be localized as a shear zone. Okay, so additional evidence that we had this thickening path to stabilize cratonic mantle comes from a really interesting texture that I love because it goes back to some work I did as a PhD student. This is looking at exsolution texture. So for those of you in petrology and mineralogy, exsolution is when a phase can take in another species in its lattice that at high temperatures, the lattice is more open. So for instance, at high temperatures in pyroxene, we can fit more aluminum, 3+, in the pyroxene structure. But aluminum is not in the normal formula. It's a non-ideal component in pyroxene. So what happens when we cool down that pyroxene is that aluminum no longer likes to fit into that more constrained lattice. And so it's going to exsolve into another phase. So we see this in like perthite, lots of examples from petrology. So in the mantle, this can happen where we have, if I go back real quickly to this slide, if we have residues that formed here, they're at high temperatures near solidus, that pyroxene in that mantle can hold a lot of aluminum. But once we bring it down to temperatures lower than 1,000 degrees or so and higher pressures, which also helps, is we will stabilize garnet. So garnet is stable at high pressures and in this case lower temperatures. And the fact that we have exsolution of garnet, which we observe in a lot of cratonic mantle pyroxenes, suggests that we had this pressure temperature change. So this is just a really nice example from a paper by Emma Tomlinson from South Africa, but this has been observed in several other cratonic mantle. So you might ask the question, well, if we just cool a static block of lithosphere, I didn't show it on the other slide, but that spinel garnet transition is actually curved, so we could actually just cool it into the garnet stability field with not really changing the pressure. But I think there's actually something more going on that's not just isobaric cooling. And this is an example, so this is not per se a cratonic xenolith, but I have seen similar examples, I just didn't have them ready for this talk, where we have garnet lamellae that exsolve from pyroxene, and they show evidence of deformation during that formation. And if we look at the garnet exsolution, so these are the extinct phases in this cross-polarized image, you can see them here. They have these strongly tapered ends to the lamellae, which is consistent with a deformation origin versus a growth origin. So this is some qualitative evidence that during that formation of these garnet exsolution features, we had something that was tectonically deforming the mantle. If this was just happening in a static environment, we may not see this sort of level of deformation. Okay, so those slides kind of talked about how do we form a craton. So we have these pulses of microcontinents accreting and suturing. We have an amalgamation phase that must involve some level of shear zones to allow sticking of these blocks. So now, how do we keep that stable? How do we allow this this thick lithosphere to survive for billions of years? So there's two ways that we can do that. The first is dehydration. So when you have a small amount of water dissolved in the mineral structures of anomaly anhydrous minerals like olivine or pyroxene, even a small amount of water like ppm level can drastically reduce the viscosity of olivine. And so because olivine makes up most of the mantle, if we make olivine wetter, we can actually lower the viscosity, allow it to deform more. So this actually plays into shear zones where if we have fluids, where those fluids came from, maybe they came from hydrated serpentinized slabs or something. If we allow the mantle to be wetter, it can deform faster. But if we dehydrate it, it becomes more and more viscous, very stiff. And so one way is to just dehydrate this mantle. And the sort of main paradigm for this is that during the melt depletion itself that formed these highly depleted Archean roots, we dehydrated all of that water, so we left behind a very high viscosity, stiff mantle that basically survives amongst the convecting mantle for a long time because it can't deform. So I'm going to introduce another idea which just got published a few weeks ago in EPSL with Sinti, where maybe we actually don't need the role of water to be that important. And if we think about just grain growth, we may be able to also effectively coarsen the grain size of the mantle so that we get it into a deformation regime called dislocation creep, where the grain size doesn't matter and it's just harder to deform a mantle that's in that regime. So this is going back to the water idea. So we did some thermodynamic phase equilibrium modeling a few years ago, and this was just published last year, where we kind of computed the water storage capacity of a model mantle peridotite. And the bluer colors represent higher water contents in the bulk mantle. So you can see that at high temperatures, higher pressures, the solubility of water is higher. But if we go to lower temperatures, that water is no longer as soluble in these anomaly anhydrous minerals. And we extended that to look at individual minerals along geotherms. So in this figure, we can see that if we think of a cold cratonic mantle geotherm, olivine water solubility is much less than 1,000 ppm or so. But for other geotherms, hotter ones, we can hold more water. So this is kind of interesting for in the Archean, if the mantle was wetter because of this, it was hotter, maybe we were able to facilitate some of this deformation. So I don't know if I have time to go into this, but this is another idea that came out of this paper where during the cooling of the mantle lithosphere as it becomes stable, if the solubility changes, we may have a repartitioning of water in the within the different anomaly anhydrous minerals. And the idea is that if olivine can hold all this water when it's hot, but now it can only hold half as much when it's cold, the same applies for pyroxene and other minerals. And what that means is that we may actually have water that comes out of these anomaly anhydrous minerals as we form these thick, cold roots. So it's this idea of water release during cooling. Initially, I titled this paper "The Sweating of the Mantle," but a lot of reviewers didn't like that and thought it was crude, so I had to change it to some much more boring title. But we actually see petrographic evidence of this. This is a mantle xenolith that shows small amounts of amphibole, which have mantle-like compositions. So we know that this amphibole had to form, somewhere at depth, that replace climate-pyroxene. And we did a mass balance because we actually measured all the water contents in these different phases in these rocks. And we found that we could actually account for this small amount of amphibole if we changed the solubility along a PT path, which we knew for this sample. So this idea is that as we cool the mantle down, the solubility of water anomaly and hydrogenous minerals changes. Some water may be released. It may form these areas that have a little more hydration. And that has actually led me to further collaborate with some seismologists and geophysicists who are very intrigued by certain weird structures within the cratonic mantle called mid-lithospheric discontinuities, which many explanations have been proposed for these velocity anomalies where hydration or metasomatism could play a role in some horizon in the mantle that is heterogeneous than normal mantle. And so one idea is that maybe as the mantle formed, we may be creating these intrinsic MLDs from this sweating idea. So a lot of other petrologists and seismologists suggest that metasomatism is responsible for these MLDs, which kind of is not really a satisfactory explanation for me, because that means anytime you see an MLD, you had to have some metasomatism that just happened to stay there and form that MLD. So this idea is that this is an intrinsic process of craton formation, that we may form these structural discontinuities. This is highly speculative. This work was recently published, and this paper argues more for metasomatism because we looked at the Wyoming craton, but I haven't really fully explored that idea completely yet. Okay, so talked a little bit about dehydration, hydration, how that can stabilize cratonic mantle. I'll come back now to that second idea of just grain growth. So this is work that we just got published very recently, so you can go read it in EPSL. So the main idea is that we may not need a lot of fluid or water. It may not be necessary. It definitely helps. So the idea is that we know we have some grain sizes in the mantle in xenoliths that are really large, 1 centimeter or bigger. And what we did was we computed some very simple grain growth laws to kind of see, as a function of temperature and time, what the steady state grain size would evolve to in a mantle. So we took steady state grain size to be about average 1 centimeter, which is borne out by the xenolith data. And this plot on the right shows the healing time, essentially the E-fold time to get to this steady state 1 centimeter grain size as a function of temperature. And we did this for a range of mantle strain rates. So even for strain rates on the low end, which we might imagine for the mantle beneath Cratons, for a dry mantle, we would, if we were even at 900 degrees or so, we could, if that mantle formed in the Archean 3 billion years ago, we could actually heal it just by grain growth alone to about 1 centimeter today. And so if you have fluids around, which is what is shown in these dashed lines, that process is even faster. So that should make you think about the failed kimberlites, because that's a way to get fluids to come into the mantle, but we may not always see them. They are interacting with the base of the lithosphere. And in fact, there's a lot of consensus emerging from seismologists too, that even the base of the lithosphere itself may be defined by a partial melt layer. So there is evidence of fluid that could be present there. So the take home is that once we get into this very large grain size regime, so you kind of know this intuitively when you go in the field and you see a fault zone or a shear zone. The grain size in those fault zones are tiny because you need to localize the stress through grain size sensitive creep. So you have myelinites, right, which have tiny micron sized grains. When you have big grains, it's harder to deform. So if we can heal the mantle to these large grain sizes just by grain growth, that can be just one way to keep it stable. Okay, so this kind of recaps the first few parts of this talk. I won't read all of this. So we sort of covered the formation, the coalescing, and how that might be borne out in different petrographic observations and textural observations. So let's talk about the damage phase next, and this sort of smaller subcycle. So that we're going to focus on the formation of these olivine tablets that are really strain-free. So just to remind you, we're going to focus on how we form these grains that grow into other deformed grains. So this is a nice example of a transitional prototype from the Wyoming Craton that we've published work on. And I'm going to show, I think this might be the same sample or a very similar one. So this is a large area EBSD map of the whole thin section. So a map like this can take 10 to 12 hours to run overnight. But we have optimized things where we can run them in half the time now. And what you're seeing, these all different colors represent different degrees of crystal misorientation. So for those of you taking petrology lab, this is just a way, if you put in your cross polarizers in your microscope and you see wavy colors like this, that means that that crystal has a lot of misorientations amongst different lattice points inside it. If you see a crystal that doesn't have a lot of, just a very smooth color, it's just a much more strain-free, more perfect crystal, so to say. So this is another way to visualize that. This is using the same EBSD data set. So we get one map that takes 10 hours, but we can spend 100 hours analyzing the subsequent data. So this is a map where we're just looking at the olivine, and the blue and red colors similarly represent this misorientation. So you can see, think of higher, warmer colors represent more misorientation. So once we go past a critical degree of misorientation of greater than 10 degrees or so between neighboring pixels, neighboring crystal orientations, then we would form new grains. But you can see all of these tablets basically have no misorientation. They're like essentially strain-free. So I collaborated with an experimental petrologist, rock deformation experimentalist, Yuval Bonet, who published a couple papers based on the Wyoming Craton xenoliths for exploring what could have been the formation conditions of these tablet olivines. So the key thing is that this texture represents an annealing texture. So it represents a period after a high strain, high stress event that now the mantle is relaxing back. And when you see this is not an equilibrium texture. It's what we call discontinuous static recrystallization or discontinuous grain growth. There's a lot of other fancy words for it. But basically, what we found is that if we compare the experiments to the xenolith observables, we can estimate things from the xenoliths like the dislocation density, and from there we can get a stress using a grain size piezometer, and that corresponds to pretty high stresses for the xenoliths that show this texture. And high stresses imply high strain rates, and high strain rates represent very fast timescales of deformation. So basically the activity that formed these textures had to happen rapidly, was high temperature, and then basically the kimberlite just had to take this texture up, and we're seeing the healing in process. Basically we're seeing a snapshot of the mantle trying to heal itself after this disturbance. So that kind of summarizes that here. The key is immediate kimberlite capture. So we don't always see this texture. It was recognized by Mercier and Nicolas in their 75 paper, but they didn't really see it everywhere. Interestingly, it's only seen, as far as I know, within cratonic mantle. We don't see this in off-craton mantle, whereas we see all the other three textures I've talked about everywhere. So the implications are that if these tablet textured transitional xenoliths never erupt, the annealing process would grow those grains out. And that just leads to grain growth, which leads to stability. So annealing reduces the stored strain energy, leads to grain growth, and can strengthen the mantle back into dislocation creep, which makes it harder to deform again. So it's kind of like the kimberlite that fails to bring these up actually helps re-strengthen the mantle. That's one way to think of it. So I kind of, if you walk away with one mantra from this talk, it's that a craton strength may be actually enhanced through these episodic traumas, these damages over time. And it's kind of like our lives, right? We have all these battle wounds after a long time, but we've survived. So, I think if you think about it, how many kimberlites never erupt? And I think this is a question no one has a good answer to. Perhaps with the stronger integration of seismology and geophysics and mineral physics with petrology, we can maybe invert for more signals and understand, things like metasomatism beneath the cratons. Okay, so I think I have some time to talk about Wyoming craton a little bit to sort of put these ideas to the test. So one place where I think this whole cycle and that subcycle has happened is the Wyoming craton. So this is a map of Laurentia, or North America. The core craton is in white here. And the Wyoming craton is highlighted or outlined in red. And the Wyoming craton is it's a weird craton. It's the poster child of a messed up craton that has been broken up or is about to break up. It's a very small craton, so it's perhaps not the best example of the most stable one, but it's a good place to study craton dynamics when cratons misbehave, so to speak. And what happened to the Wyoming craton was it was severely affected by the Cenozoic laramide orogeny. So here's a map of some more details of the Wyoming craton. We're going to focus on two kimberlite localities, the Williams kimberlite, which erupted closer to the edge of the craton, and the Homestead, the areas are a little approximate just to highlight, and the Homestead xenoliths, which erupted a little bit away from the edge. So it's thought that during the Cenozoic, late Mesozoic to Cenozoic, we had the impingement of a large oceanic plateau or some other way we had the Farallon slab becoming much more shallow. That began to plow through southwest Arizona, and it's thought this is a plate reconstruction geodynamic model that shows it going all the way to the Wyoming craton by around 65 MA. And around 55 MA during the Eocene, this is when these kimberlites erupted. So that's also important to remember that these kimberlites erupted just as we think this slab was just like, maybe reaching into it. So within the Wyoming craton, so we're just focusing on these two areas because they have abundant xenoliths. What we saw is that within the Homestead kimberlite, we observed predominantly textures that were protogranular and equigranular with very few deformed porphyroclastic ones. So we thought maybe the Homestead, whatever mantle the kimberlite at Homestead sampled, it's sort of a completion of the cycle. We didn't see any of these transitional textures. But at Williams, we saw many samples that had these tablet olivines. So that's kind of interesting, and we'll talk about an idea for why. Okay, so I should have showed this earlier, but this is kind of what we use for EBSD data. And when we do EBSD data on xenoliths, the skeptical structural geologists here should be worried about how do we even know, what direction corresponds to a shear direction, right? Because a xenolith is like a meteorite. We have no kinematic reference frame. Whereas like if you go to an outcrop and you measure a shear zone, you know where, you know the absolute reference frame. So olivine is also helpful here because thankfully with its orthorhombic symmetry, we have a very predictable we have predictable ways that it can slip. And so we can actually look at individual olivine grains and measure things like the subgrains, which are just basically the same process of dislocation creep happening, but on one grain. And if we can pinpoint what that subgrain boundary is doing, we can actually infer a slip system for that grain. So ideally, when we do EBSD on many, many grains in a sample, we plot all of those orientations on one pole figure. We would get something like this if we make some assumption about what we think the shear direction is, which is often very difficult for xenoliths. If we do the same thing for lots of individual olivine grains that have subgrains, we should hopefully get the same answer that we get for the bulk rock, because that means that this rock was deforming under conditions where we would yield the same active subsystem would be active. And olivine is great because there's been lots of experiments. It's orthorhombic. We can understand it. There's only so many ways it can deform. So there's been a lot of experiments that have, for instance, parametrized the amount of water that's dissolved in olivine as a function of stress. And different types of olivine crystallographic preferred orientations or fabrics evolve with different water contents and stresses. And so, we can get all these different types of fabrics that correspond to different slip systems in olivine. So that can tell us something about the geodynamic state of deformation. We need to highlight, though, that all of these experiments assume a simple shear strain geometry, so something like an mid-ocean ridge, simple plate moving apart. And, beneath continents, that's probably not an accurate strain geometry. Things are much more complicated beneath continental regions. Okay, so nevertheless, there's no additional experiments we can really use for more complex strain geometry, so we still apply this to things like xenoliths and even meteorites, which is even scarier because we have no idea whether they behave the same way. But this, should be future avenues for experimentalists to explore different types of olivine deformation conditions. So I'm just going to show one representative sample here, and we're not going to march through all this data, but because we don't have time. But you can read this paper that came out a couple years ago. So the long story short is what we saw is that between the Homestead and Williams xenoliths, we saw some very discrepant things. We were hoping that when we mapped the entire sample, we would get the same answer as when we get the subgrains, but we saw different fabrics emerge. We found no transitional textures. And we also measured water content through SIMS in all of these olivine and pyroxene grains as well. So we did conclude that the Homestead xenoliths did reflect wetter conditions, but the sort of CPO subgrain stuff didn't match up. At the Williams locality, which is slightly more to the edge, we found similar discrepancy, lower water contents, higher temperatures also, and more of these transitional textures. So I won't belabor this too much, but the idea is that why we didn't see things match up like we see nicely in other peridotite locations probably can just be explained because we're really the first ones to do this really detailed subgrain analysis, and it just shows that these continental regions are just not in simple shear. There's a much more complicated strain geometry that has no experimental counterpart to compare to. And also, we may be at a threshold where the water content may be flipping between different subsystems. So if we go back to what this means geodynamically, so I want to leave some time for questions, is if we put these two xenolith kimberlite localities that erupted in the Eocene back into context of how the cratonic margin evolved. So if we go rewind back to 90 MA, this is when we still had normal subduction. The Farallon slab was doing its thing. The Sierra Nevada batholith was growing big arc. Out in the Wyoming Craton, it was just happily hanging out, not doing anything. Then 80 to 75 MA or so, the laramide orogeny kicks in. We get this flat slab, which now is actually pumping lots of fluids and water into the deep lithosphere. And there's actually a paper we have in review right now that can explain some of the uplift of the Colorado Plateau by lower crustal hydration. And so if it's true that the flat slab extended all the way to the Wyoming Craton, we may expect that the Homestead locality, which is a little bit closer into the interior, may have seen a little bit more hydration, which is actually what we see in the olivine water contents, pyroxene water contents. And the Williams sample was a little bit away from that. So where I think it gets exciting is right at around 50 MA when the kimberlites erupt and pluck out pieces of the mantle which will become the xenoliths we study. So around this time, subduction ended. Things became very complicated. It's thought the slab maybe broke off. Who knows? But we know that something happened to the Williams mantle where it deformed very rapidly under high stress, high temperature. One idea is that maybe a drip happened. A stenosphere came in, and basically sheared off the edge of the cratonic mantle. And the edge itself is where we get these more geodynamic instabilities, convective instabilities anyway. The Homestead xenoliths may not have seen as much of that, which is why we never observe those transitional textures. So this kind of summarizes that in a lot of detail, but basically the idea is that we might have a complicated scenario where the kimberlite at Williams sampled an evolving lithospheric drip that was deforming, and we just happened to capture these tablet xenoliths, but at the Homestead locality it was just sampling a normal background mantle deformation. So I want to just highlight that idea is not super crazy, because even today beneath Nevada, seismic anisotropy studies suggest there is a drip going on beneath the Great Basin. And this really nice work by Nick Dygert and others showed very similar highly transitional textures and porphyroclastic textures from Lunar Crater, which is kind of within the area of this, this drip, suggesting that maybe this is ongoing today in some areas beneath the western US. So we think something like this probably happened sometime in the Eocene during the waning stages of the Laramide and the kimberlite eruption. Okay, so I'm going to end here with a few take-home messages. I think the key thing is that Cratons are more exciting than we think. I have this idea that through the traumas, the kimberlites that fail to erupt, the metasomatism, that actually can strengthen Cratons. That leads to grain growth, which ultimately heals the grain size and makes it harder to deform. And the awareness of this transitional texture, which is something I'm continuing to explore in other Cratons, is something that I think we can link to the kimberlite xenolith connection, and understanding why do kimberlites erupt where they do, why do they bring up the sort of xenolith textures that they do, and I think that's kind of the future work here for that. So yeah, hopefully we have some time for questions. Thanks.
Question? Should we start with the student and then Laura? Yeah.
Thank you, that was awesome talking. The alkali melts that you mentioned earlier, do they typically, do they happen in the annealing phase also? And kind of where along the slab do you think they happen? And do they have a mantle geochemical symmetry?
Yeah, that's a great question. I think I had a PT diagram somewhere back here. So the whole alkali magmatism thing is really intriguing. And in the Wyoming Craton, right, there was this whole Montana alkali province where you had lamproites and stuff that aren't really kimberlites per se, but they're weird. So this diagram on here might show some stability fields for things like amphibole and phlogopite, that diagram on the left. But that's a good question. I think you probably have. So I'm now convinced that a lot of seismologists are right, that there is a low-degree melt layer that defines the LAB, the lithosphere-asthenosphere boundary. That melt may never really come out. Sometimes it might, and it may be easier to get out on the edges, right, of the craton, because you have ability for upwelling a little bit. So that's the asthenosphere-derived stuff. Then there's also the group 2 kimberlites, or whatever they want to call them, which are things that are thought to come from the lithosphere. And those are things that we don't really talk about here in this talk, because that you need a weirder mantle to form those. You need amphibole, mica-rich, more peroxenite-rich lithology. So I'm kind of talking about base mantle that's olivine-rich, that's modified by ultimately asthenosphere-derived melt. They could be lithosphere, but it's hard to tell. And if they are, we might see those in more exotic kind of xenolith assemblages. But yeah, that's a whole very interesting question, which unfortunately I think a lot of us are still working on.
Very nice, thank you. For a simple question, you have the ecogranular and protogranular types. Are the olivine grains the same size in both cases?
In some cases, they can be, but usually the protogranular is much more larger grain sizes. Yeah, we haven't really seen, an ecogranular xenolith that's got all 1 centimeter It's more about the morphology of the grain boundary or the phase boundaries. But yeah, that's an interesting question. So the protogranular texture itself could also be stable, right? Those large grains could just, they never, some of them are evolving to triple junctions, but the fact that there's curved grain boundaries means that the grain boundaries are migrating. So we know that's happening at like a high temperature, resonance in the mantle somewhere at static conditions.
Granular ones would be weaker than the protogranular ones.
They could be, yeah. Yeah, that's a
The
good
other
point.
question I have is like, the way you thicken the craton, let's take a look at your diagram there, that's like figure 2 in your
Yeah.
paper. So you're thickening the craton by a series of faults. Of course, the faults are weak. And as you go deeper into the craton, temperature goes up, and you've got fluids going on. And you've raised an interesting point in your paper that the fluids, rather than weakening things, could strengthen things by enhancing grain growth.
Yeah.
Anyway, so your grains are growing. So closer to the top, the shear zones are weak. Deeper down, the shear zones get strong.
Possibly.
Must put a limit on how thick your craton can be.
Yeah.
It must lock the whole system up. And you must have, so once your crystal starts getting large, and it's strong, you can no longer thicken that part of the craton.
Yeah.
Your fault has to jump somewhere else,
Or it just dies, right.
To have a series of pervasive faults throughout the craton.
Yeah. No, that's a good point. And maybe that does limit the thickness. So, maybe 300 kilometers is like really thick for that process to happen. I haven't thought of something that goes that deep, but probably not. But there's probably, I don't know because if your logic would also apply to faults in the crust. Why don't they just stop too if this process of, so it's like you're balancing, during dynamic recrystallization, you have to balance the grain growth with the deformation. So that's why you can maintain small grains, because you don't always, if you take away the deformation, then you can anneal and grow. So you need to take away that. So while the faults are still active, it's hard to actually grow large grains. It's once you allow recovery to happen, then it's when you can lock it up. So your question is, when does that transition happen and how deep? It could be.
Yeah, just follow the path. Check only one of those faults going down from the surface.
Right.
Just follow one, keeping things simple. With that, I guess what I'm saying is that when the grains what I'm asking is when the grains get larger, could that actually stop the deformation or slow it down to the point where annealing could enhance and strengthen things further?
Yeah. It would depend on a lot of things, like what we know about the strain rate down there and stuff. So I don't have a great answer right now, but conceptually, that makes sense to me. So it would put a limit on this, because we know that this doesn't keep going. So it's also interesting. In the Phanerozoic cratons, we never can form stuff this thick.
Right.
So is that because we just, maybe we lock up? In what you're suggesting happens post-Archean, but in the Archean, maybe it was a little bit different.
So why would the Archean be so different from
Well, we had a hotter mantle. You're the expert on that. It could have been wetter too. So, that's an area where I'm really starting to dip my toes. Like, I'm not an Archean person at all, but kind of studying this has made me wonder about a lot of the Archean rheology. Yeah.
So thank you for the talk. I learned quite a lot.
Great.
This is very new to me. So when you were linking it with planetary, I'm wondering, very different environments, let's say on an asteroid or what we think happened on the moon, how do you see these approaches, these skills, translating
Yeah.
to those very different areas?
So I think that's where it gets really exciting, because we know, like, in some ways, other terrestrial planets that have similar, like, silicate mantles, it's kind of like a blank slate. So I think we can actually approach those areas with more of an open mind, where here, you know, in the mantle, we're like constrained by a lot, and we try to fit everything to everything. So, you know, I think that's where the experimental is also going to play an important role. So I actually know Nick Dygert quite well. He did a lot of work on lunar mantle overturn and the role of cumulates and ilmenite. And I think that's really interesting because, you know, just thinking about a simple mantle system like that is possible. And it's, in some ways, you know, maybe it's hard to test, but at least we can make predictions that we otherwise are a little bit forced to make work on Earth.
Yeah. In some ways, it might be easier to test if you have in some ways, a simpler system.
Yeah, so like the moon is kind of a cool one where there's really like two phases, right?
Yeah. Or an asteroid like Vesta.
Yeah.
Where it's a much simpler, smaller body. We don't have to worry about pressure as much.
Yeah, so I know, like, terrestrially, you know, this has been a lot of stuff that kind of came out of my time at Brown, but the thinking on olivine is starting to change because, you know, we really had this paradigm that works for mid-ocean ridges, and continental regions are a whole other thing, but we can now do, like, better experiments, things that involve other phases. So that is ongoing. So I can see that, you know, possibly also branching into the planetary world where we might have weirder phases to deal with, you know.
Thank you.
Yeah. Yeah.
I don't know, it's a great talk, and I wish I'd seen it before we had a chance to meet this morning. Another comment is that the area that seems missing in Antarctica, we should talk, because there is this like really fantastic set of samples.
Yeah.
To James Day about some of them.
Right, and you would be the expert on the Antarctica xenoliths.
Office that
Cool.
show a lot of the deformations like what you showed, so really interested to continue the conversation. But I do have a question about the relationship in age of some of the deformation fibers. So you showed some age constraints at the end, and do you see relationships between lithosphere stabilization ages and these deformation fabrics or textures? And if you could use that to help sort of build this story of,
Yeah.
you know, Craton growth and stabilization.
Yeah, so I think that's my next step. I'm writing a big proposal right now with a whole bunch of other people where we want to explore this. And I think it comes down to looking at the kimberlites and the xenoliths together, because we can actually date the kimberlites. Well, we have datable things in the kimberlites, so we know their emplacement ages. So we know that at that age, when the kimberlite erupted, it sampled mantle that has this texture. So I think that's the key thing, that no one's really thought about combining the two. And then if we think about things like plate reconstructions deeper back in time, which get iffy, of course, but also just looking at surface geology and the surface geology. So Wyoming is great because, like, we know so much about it, the Wyoming province. But I would love to do this for all the other Cratons where we have good age constraints for the kimberlites. We know the textures of this mantle it's sampled really well. And, you know, we can then put it into a regional tectonic understanding of what happened during, you know, of course we're talking about hundreds of millions of years, but that is still a lot a better constraint than saying this kimberlite erupted and, you know, we don't know why it did. So that's kind of my next step, and hopefully that answers the question that, you know, it's like the next direction.
I think I'm also thinking of like with xenolith ages as well. So like using like melt depletion ages.
Oh, like rhenium-osmium. Yeah, those are, I mean, I think those only work for xenoliths that are truly melt depleted. And they only tell you about the melt depletion. So anything else, you know, it's so hard to date the deformation. So that's where, you know, this is like geochronology adjacent in a sense, because we can never get an absolute age on anything, but we can understand the process and have some time constraint. So like the grain growth is one step into that. But yeah, like lutetium, hafnium, and garnet could be another thing, but then you need other minerals to have a good isochron, and then everything is like possibly reset by the eruption. It's like isotope geochemistry in the mantle is just terrible. Yeah. All right.